Okay, guys, take a second and recognize where we are, just in terms of history. For the first time ever, power and compute is coming together. It just happened, and it's never happened before, and this is the only first time, and we've got a front row seat. And I know things are super busy and new things are happening every week, but I think it's worth sort of sitting down and acknowledging what we're getting to witness.
Yeah, it's incredible. I love that the last time we spoke, which was just a few months ago, we were talking about the power and how that power and data centers, and it kind of took a turn around training. And if I think about the biggest innovations in the industry in the last few months, we had, of course, OpenClaw, NemoClaw, this Agents 2.0. When you look at inference, the way I used to use a model is I would ask ChatGPT a question, and that was it. And then I started to, once we got reasoning, I could ask a question, and it would consume more tokens, and then it would drop off. And so it was spiky, but the spike started to get longer. And now with claws, like my claws running 24/7, the people who are finding claws useful have them churning through tokens. And so really quickly, you get the spike that's not dropping off. It's just a complete flat line. And so, there's so much innovation at every single part of the stack. It is crazy to see how rapidly things are changing. It definitely feels like we hit some sort of escape velocity.
Yeah, I mean, this is like an infrastructure project that we're talking about, and that's where I think that the parallel between, we use the term intelligence factories, right? That's what these new data centers are producing. It is the next layer of infrastructure instead of the atomic unit of whatever that industrial revolution being an electron. In this case, of course, the atomic unit is a token, and that's tokens can be applied now to a wide array of things. They're going to be applied to medicine, to of course producing software, for entertainment, for everything. And so our sort of initial question to you as the power expert here is, what is the relationship? Why is power even part of this conversation when we're talking about in this case, the cost of intelligence?
Yep. So I'm obviously biased, but I think power is super important. First of all, you can't run these things without it, right? So it's the input to the factory. Second of all, to run it, we need to be able to produce the power somewhere, and then we need to get it successfully to the GPU to produce a useful output. So we need to think deeply about where that energy comes from, because it has a cost associated with it. And then how we transport it also has a cost. You lose stuff along the way. There are efficiency losses. And the more we lose, the less reaches the chip, which means the less token, the less intelligence output we get.
Efficiency, when it comes to how you're delivering it, I think that there's a number of different ways that can happen. But when a lot of people are looking at, for example, producing these token factories, and you're trying to measure the sort of like cost or the total cost of ownership of these token factories, aka data centers. Can you dive in a little bit more about where power plays into that equation of the cost of ownership, as people are looking, maybe they're deciding this gigawatt factory, right, that I'm producing, and I want to decide like what to put inside of it. Obviously power is the input, but what is the relationship between power and the chips themselves and the data centers?
So that's it's a really good question, and maybe I'll take a step back and reference our previous conversation. We talked heavily at that time about training because that was what was dominating the conversation. Today, I feel like things are shifting to the inference side. So Nader mentioned how his usage went from being very peaky and spiky to being more broad, and I think the same thing is happening for all of us. It's like the early days of the electrical grid. Initially, we only have lights to turn on, right? Like the first grid that was built in New York, we only had lights to turn on. So then, when we didn't use the lights during the day, there was really not much usage. Now we're finding other things to do with it. So we're kind of, flattening on that usage, and we're keeping these factories busy. At the moment, it feels like we're going through a bit of a discovery cycle to figure out how to appropriately price what we're doing, right? Like the factories, our AI factories, are producing tokens or intelligence as outputs. And different people are using different metrics to value those productive outputs, those tokens. And as with any factory, you need to know what the product is costing you to make in order to be able to sell it, right? Like if you don't know how much it costs and you're just selling it, you may be selling it at a loss, which may be okay in the beginning, but long term, it's not good. It's not sustainable. So, figuring out which metrics to use to value a token is really, really important. When I build an AI factory, there's a bunch of money that goes into it, right? Like there's a CapEx allocation, and a certain amount goes into chips and racks and cooling equipment and power equipment and other things. Once I get past the building stage and I start operating, my OpEx is dominated by energy usage, right? So as I'm churning out tokens, the primary input is electricity. That electricity is going to various things. Some of it's going to, the chips, which are putting off heat, as well as some of the equipment along the way, which is also putting off heat. And then we have to use some of the electricity to then remove the heat from the building to keep everything cool. And in the ideal world, every watt we put in gets to the chip, but we can't really get there. And today we're, in most data centers, we're pretty far from it. Some, cutting edge hyperscalers that are getting pretty close, so that overhead is only like 10%. But for most data centers, there's still a lot of overhead, and we're wasting a lot of energy doing other things, not producing tokens.
Yeah, I think it's really important.
Yeah, I really like the way you framed this as if your business is selling anything, you should know what your costs are. And so if your business is dependent on or generating tokens, you should know what those costs are as well. And I hadn't really thought about how much energy would make its way to a data center, but then not get involved in in token output. And you kind of mentioned hyperscalers getting 10% overhead, right? So that means that the lot that you put all the power in, and only 10% it's going to not powering the compute or generating the tokens. What does it look like for, let's say, maybe a less effective data center or a smaller data center? Like, I'm just curious, like, what could the range be of efficiency?
I think probably the most inefficient data centers are like 100% overhead.
Really?
Yeah.
So 100%?
Yes. I think there's a PUE number of 2 in a data center somewhere.
Right? Like a PUE number?
So it's an efficiency number that's used to measure like overall efficiency of the facility, accounting for everything. So if you're putting, 1 unit of electricity in there, how much is actually, reaching the destination, what it's supposed to be doing, and how much is reaching IT load versus going to other things like cooling. And
IT load being generating the tokens?
Yes. Yeah. But a typical, I think what's more typical is something around 1.2, 1.15 or something like that.
That's crazy. I didn't realize it could be, like, I guess if it's not planned well, and if you're not putting a lot of effort in reducing that overhead, it can literally be double.
It's a worst case scenario. I think that would be, record bad, but it happens.
Of course it happens. Yes. Yeah. That's
crazy.
This
is where, a lot of the work that, NVIDIA is doing, like around DSX that just came out, is that, for the first time that many different suppliers oftentimes meet is inside the data center, but that's way too late, because then you have a lot of this overhead. That stuff needs to happen so much earlier. You were describing it. I think the factory parallel is just perfect. And you can imagine if you were assembling a physical good, and the first time that, the person who's doing the introduction of the materials, to cutting it, to preparing it, to the person who's actually assembling it, if they all start talking for the first time already on the factory floor, then there's going to be a ton of inefficiencies, which is why you need to, of course, simulate everything ahead of time. You need to have extreme co-design in the actual chips themselves, that, everything from the networking to the memory to the, cooling, and to make sure that everything, when it comes together, you've thought about that problem as a system problem, which it really is, so that you bring that ratio down.
And DSX, for anyone not familiar, is NVIDIA's gigawatt factory. It's essentially, we're building our own gigawatt factory. It's a new scale. There are new problems, like Carter just mentioned. And so the way that we want to essentially help the ecosystem is by attempting to just do it ourselves, see what software we need, what solutions we need, and then see how we can give that to the ecosystem so that they can build these token factories themselves.
So that you don't have to relearn at every new site.
Exactly.
Makes sense.
Yeah.
So we're kind of flirting around this idea that really what matters when you're talking about from a business perspective, whether you're the one building the data center, you're the one purchasing these accelerators, you're the one consuming it at the end. If you're a consumer, you care about the cost of intelligence. Is that certain metrics, common metrics that some people use today, for example, would just be looking at, for example, the cost per GPU hour or the number of flops per dollar, is actually probably not the right metric. Can you explain why something like the cost per token is actually something closer to what you would want to look at?
Yeah, I think that's a really good point. The electricity industry, the energy industry kind of went through that same learning. So if I only value the cost, the OpEx side of things, right? Like if I said electricity only costs as much as the fuel that I put in, plus, the people that run the plants, and like maybe some other operational components, then I'm going to end up undervaluing that electricity unit because I didn't account for the CapEx investment that I made up front. So essentially what we do is, we have this number that is very flawed, but that we use in the power industry, that is called levelized cost of energy. So we have a sort of a
cost of energy?
levelized cost of energy. It really is a terrible metric for a variety of reasons, but it's a very simple one to think about in this context. So essentially what we do is we say, how much capital did I put into building this facility and this infrastructure? And how long is it going to be run and be productive? And then I look at all the OpEx over the life of that asset, and I add that in also. And then I divide by the amount of units of energy that I'm going to produce. And so then when I do that, I get a levelized cost of energy, something that helps me understand over the life of the asset how much it will cost me to actually produce each unit. And I think if I look at a GPU hour, it is a time-based metric, which doesn't account for inefficiencies in electricity production, delivery, processing. It doesn't account for any of that. It just looks at time purely. And I think we need to move the industry to a metric where we account for those inefficiencies. Otherwise, we won't value the product out of the factory appropriately, and we'll end up selling it for the wrong price.
The values that's coming out of your margins. If you're not aware of it, you're eating the cost essentially. Yeah, interesting.
That's why I think if you, I can flash this equation up on screen, but if you divide effectively the cost of GPU per hour, a time-based metric, by something like the number of tokens you can produce over some time, for example, the number of tokens in an hour, all of a sudden then you can actually get the cost per token. And then you're starting at looking at something that really does measure the output. It's like the cost per electron, but in this case, the cost per token. Another one I think is, we can flash this up on screen as well, but effectively the Pareto curve, and it's looking at how many tokens can you get out of, for example, a gigawatt facility. And that way you can start to, compare apples to apples in that sense and say, okay, we're in a power constrained world. There's only so much power that is going to come into this data center, providing we don't do it at something really expensive and try and change it. Let's say it's static. This is a 5 megawatt data center. I want to get the most tokens out of that thing as possible. So the tokens per megawatt is the sort of ratio, the metric that I think makes a lot of sense.
Yeah, it's like you almost have to have awareness of everything below the model and above it, right? Like if I'm going to generate code today, right, that's going to generate a lot of tokens, like how much did that code cost me is a question that has to be walked all the way to the wasted electricity that entered the data center that was then used on the chip, which then generated the tokens all the way through, right?
Absolutely.
That's crazy.
and humans should be good at this because we've done it over the years with different products. We know from an agricultural society, we know the same thing, right? Like if it costs us a lot to get the seed or the water, right? Like if we are carting the water in on a truck and the truck's leaking half of it along the way, or we're piping it in and the pipe's leaking.
Yeah.
Like all of those contribute ultimately to the cost of the food product or to the thing that comes out of the factory. So if we go back to the equations, which is fun because it makes it easy to think about things, the way ultimately to reduce the cost of a token, there are a bunch of levers I can pull, but the big ones are I can either try to reduce the capex, of the facility in general, which you do by standardizing a design and modularizing it, what you guys just said you're doing. The other thing is you reduce the OPEX. So I make the electricity input less. I reduce other OPEX related numbers.
The overhead.
Exactly. Or, if I go below the line, I can increase the number of tokens, right? If I make more tokens, so if I can make them faster, or if I just like crunch the utilization rate of my factory. If my factory is sitting around only producing half the amount of tokens that it could be producing, it means my cost per token goes up because the numbers of, the other numbers stay the same.
Yeah.
So
I guess that's why NVIDIA invests so much also in the software layer, because if you, for example, with Dynamo, you can do things like disaggregated inference, you can do some really interesting optimizations that then are also just churning more tokens out for the same amount of power.
That's what I think. If you look at between generations, this is where, and we can flash up a chart here as well, showing the difference between, for example, the Blackwell advantage, the current SKU, and then of course Vera Rubin, which is upcoming, but on this chart is the Blackwell GPU, the NVL72 compared to the previous generation of Hopper, and just comparing flops, flops of one to flops to another, you're not looking at as big of a difference than when you compare the total performance, because what happens between Hopper and Blackwell, not just these software things, but if you increase the power efficiency by many X as it did, the total flops, of course, by a couple X, and then the total throughput as well, you start to get these factors. And then you move towards something like the Vera Rubin completely liquid cooled and cooling at like 45 degrees Celsius water, which we talked about last time, cooling at 45 degrees Celsius water, and with a closed loop system, no air cooling, you start to say, oh, wow, not only are we increasing the amount of tokens at the current amount, it's also per essentially flop drawing way less power. And then you can get those massive increases over time when you're comparing against tokens out versus energy in.
I think it's very exciting because it feels like we're still very early in the curve of utilizing these tokens, right? It's the early days of the grid, and we have lights and we're starting to turn on some other things, but we're not anywhere near, we're going to reach a point where it's not just spiky with some plateau. I suspect it'll be like the early days of the internet or the early days of the grid, and you'll end up with just, full utilization of all of these facilities all the time.
Yeah, and maybe if for people watching, like an appreciation for how the spikiness changed in the internet, that was part of a lot of movements around, like I think it was like 2015, where the internet was meant to be this like, oh, I'm going to go access a quick HTML file on a server somewhere, quick, boom, download. And then we had stuff like Netflix, where it was like, actually, I'm just going to like flood this pipe with content and I'm never going to stop. Right? And that was just a complete flatline. And I'm just thinking about like token usage, even at this company, right? There are some people, like we each have a claw running. We have 2 claws for Brev running. And so we're starting to see more flatline token usage, but in a small part of the company. And it's really exciting to see claws starting to take over. But what happens when every employee has their own claw? Every team has their own claw. Like it's just going to, it's going to be an exponential takeoff in how much token usage we're going to have.
So you guys are forcing my industry to change very rapidly. An industry that is not like to change and hasn't really changed much in 100 years, because if we increase the token usage and we continue to increase like power usage in general, if we don't match on the power side what you guys are demanding, then you'll end up with a shortage, right? Which will spike prices, which is not good for anyone, because we want those, like the tokens are useful. We want to do stuff with it.
Yeah, and that's actually a really funny point. I mean, we've known each other since 2015, so over 10 years. And it's funny because you've always been in the energy industry and I've been in developer tooling. And so there was no reason for our worlds to match. And then like suddenly we're here making the same video.
We tried. I don't understand what you say.
Yeah. It's, I really liked the farming analogy, or like the food service analogy that you brought up, because I think a lot of times, humans can be very domain dependent, right? We like know a thing, but it's really hard for us to transfer that learning to into a different domain. And I feel like the same thing, right? Like it'd be crazy to think about trying to sell produce, but like, hey, we're going to do it and completely ignore our transportation costs, right? Like that's actually crazy. And especially for the way, just you have to consider all the margins through the whole supply chain. And just seeing that we're barely figuring this out now from the token generation side, while every single part's exploding. We're talking about the use cases exploding and the token use, but also the size of our data centers, the way that we assemble the GPUs on racks. Like every single part is going through, honestly, a pretty uncomfortable transformation. Like it's not easy to change your coding habits from like, I want to personally handcraft every line of syntax to like, I just asked my Claude to do something and I'm like delightfully surprised that it figured out, reviewed it, QA'd it, and deployed it. And I'm like, all right.
Yeah, no, I think that we have fundamentally, an unlimited demand for intelligence as a species. And we live in a power constrained world. And, as much as NVIDIA is innovating every year to create those way beyond Moore's Law speedups, it's funny, I can also maybe put this graph up on screen with Open Router, but essentially the number of tokens, the demand for tokens has been, growing by many orders of magnitude, definitely every year, if not, every couple of weeks, it seems. And so you can see the graph. It is a very strong exponential in the amount of tokens are consumed. And so even comparing that against the total number of flops that are being deployed across every company, accelerators, like we are growing the number of flops significantly slower than the demand of intelligence is increasing. And so that's where I do think it becomes incredibly important to think about, the TCO, the total cost of ownership of these things, exactly at that layer where I think it's like the inference iceberg. I can throw that up on screen, where if you think about it purely at like the cost per GPU per hour, that is missing so much of the nuance of what actually is going into these. And as you move down the iceberg, then you start to see things like once you go all the way to the bottom, you see the actual like, okay, how many tokens per megawatt am I getting? Because that's the real metric you want to look at.
That's the real metric. They need to be tied together, is my view. Otherwise, if you stick with a GPU hour, essentially you're saying that a token produced at a factory where they lost half of the energy on the way there is exactly the same and has the same value as one at a hyper efficient factory, which is not the case. If you're running the factory, if you're the owner of the factory, selling tokens at the same rate as someone else that doesn't have the same amount of losses as you do, your factory's going to go out of business. Yes.
Yeah, not just mispricing it like that. Tokens now for so many businesses are directly tied to their revenue. And so if you are producing less tokens, not just pricing them wrong, but less tokens than let's say a competitor in your space that is using and can produce more tokens, then that's another angle where I think you just become uncompetitive. Like you need the most amount of tokens at the best cost.
Yeah, and the insatiable demand for tokens is kind of obvious when you think about it. Like if you could have a task done and someone says like, hey, should I think about it not too hard? And it might get you worse output. Like, no, of course. I want you to think about it as hard as you can, guarantee me the best output. And for a lot of these coding tasks, especially with like a claw, that's the interface for it to go and develop a lot of this. I don't care how long it takes anymore, right? I'm not sitting there waiting on the IDE, waiting for it to get back to me. I just want it to go and do the best job it can. And if that's going to take a few hours, if that's going to come back to me tomorrow, but it's better, then I'm okay with that. And that means that it's just churning through every level of that.
Yeah. I mean, we definitely have our different workloads, right? Like I have things like that I wanted to think about deeply and spend the time on. And when I come back to it, I want it to be a good answer, right? Like I don't want it to throttle and hold back. Sometimes I just want a quick answer. Yeah. And if I want that quick answer, I don't want it to take 5 minutes. So even if there's a way for me to tell it, just give me a quick answer, I don't want it to get stuck at the data center because there's a power throttling issue, Yeah.
We're already seeing it, right? How many of your favorite AI tools or have lowered limits or have increased the amount of subscription you have to pay per month? And that's not necessarily because the cost to produce the individual token has gone up. It's actually quite the contrary, but they just have such little compute available to them at this time for obviously both training, but of course for inference even more so, that they have a really hard resource problem on their side to say, how do I serve everybody the level of intelligence that they want when I do not have enough compute? And you look under the hood, why don't they have enough compute? A lot of it comes down to getting data centers up with the power that they need to power these things is quite difficult. Yeah, it's like you can look at this as the Pareto curve again. Basically the amount of tokens that you can get in, let's say, a gigawatt or a megawatt factory, and then the amount of the tokens per second you can apply to an individual user, and that would be the more intelligent version of the intelligence that you can deliver to an individual user. And then you look at some of the things like the LPX plus Vera Rubin rack that is being announced, and it bends the curve to where you're actually able to give incredibly fast inference by leveraging the best parts of both. And of course, basically getting that the bottom of the equation, right? The cost per GPU on top and the tokens per GPU per hour on the bottom. And it sends that tokens per GPU per hour, in this case, GPU plus LPU, insanely fast, like tens of thousands of tokens per second. And then all of a sudden, okay, now we can bring the cost of intelligence through the floor. And if you just look at sticker price again, you completely miss that.
I think, for, my simple mind, it's remarkable how similar this is to just, any old factory, right? Like you've got the processing that happens in there. You've got to bring stuff to it, the raw materials. Once you start processing it, you don't want to have a bunch of wasted materials. I think we kind of joked around the big sheet of metal and you're punching out like one cup and you're throwing the rest of it away. You want to avoid those things, right? Like we've understood this inherently as humans over time, and it's a bit more abstract now because it's all happening in the cloud, like in sort of in a more abstract way. We can't see it. We can't see the material going in the bin and a truck driving it off. But you guys can see it on your end, right? Like the data centers can see it on their end when the raw materials come in and only a certain amount gets processed into something that someone is willing to pay for. Right? And I think they're trying hard to make sure that they can squeeze out more cups out of that metal.
Yeah, I like the way, even just the contrast, right? If you have a data center or if you're operating your token factory and you're losing so much and unaware of it, when your competitor is operating it efficiently, you're going to go out of business. I think just the big takeaway for me, I think, is understanding the holistic image of what in order to actually calculate your margin. Like if you don't understand holistically or through the stack or essentially the extreme co-design of understanding your supply chain in order for what the cost is of your good, then it's a huge miss.
Let's go build some efficient data centers.
Yeah. So maybe even just to think through the exercise of that, we want to build an AI factory. Like, what are the levers or where can we make optimizations? I know, the Hopper GPU or Hopper node had 8 GPUs per node. Now we have NVL72, where the rack is effectively a node. You have all the GPUs on here, CPUs here, then storage, and then you have essentially the bottleneck becomes the networking between those components. And so we've taken the node optimizations and made that higher. Then it's network optimizations, and there's a whole body of work on just that. What are the other levers within the data center?
Yeah. Well, let's start outside the building, and where I like to start.
Yeah.
And say, how do we make the power? How do we produce it? How do we generate it? And there are obviously many, many different ways for us to do it. Like we have, coal-fired power plants, we have nuclear, natural gas, a whole array of choices. Typically what happens is we make decisions based on where we are. So, a data center in Texas is almost certainly going to be running primarily off natural gas, if there are constraints on the grid. If I went to Europe and there's a constraint on natural gas, there are going to be other sources that feed those data centers. It might be nuclear. If it's in France, it might be coal. If it's in Germany, it might be more offshore wind if you're in Denmark, or
geothermal in Iceland.
Geothermal, right? Like you kind of pick your resources based on what's available in that specific area. new technologies that are coming online that are of particular excitement. But we've known about nuclear for a while, and we're decent at doing it. We need to streamline deploying it, but there's a lot of interest lately in metal fuels. So humankind spends a lot of time and energy producing metals, and then we recycle them a couple of times, and then they kind of lose their use because they're not pure anymore. Well, we've kind of figured out ways to get that energy out of the metals, and there's lots of it around. So that's like one exciting new area. Geothermal, we're getting better at. Typically, you could only do it in specific areas. We're getting better at tapping into that, and like more generally in the US. So I think there are going to be lots of things on the power generation side that will help us be able to build data centers in more places and produce power more efficiently. Then there's the transportation layer. Right now I've made it, I got to get it to my factory. We talked last time about 800 volt DC and a move to a higher voltage power systems. And that's another important one. I think there are several NVIDIA articles that talk about the efficiency gains that you could get through this. But it's not something that originated at NVIDIA essentially. It's something that started 10, 15 years ago by sort of a get together of the hyperscalers. They said, look, we need to make data centers more efficient, and we need to sort of open source the design a bit. We started a project called Open Compute, and they've been innovating in that space to achieve that goal. And the 800 volt DC concept really came from there, but it was struggling. It wasn't really gaining a lot of ground. I think some companies were using it internally, but it wasn't widely used. And then NVIDIA announced, we're going to build racks this way. We're going to make it more compatible with the general supply chain and equipment that's out there. And I think that those 5-10% efficiency gains, those little leaks that you're just plugging, in the long term, they're going to have a huge impact on your OPEX, which will have an impact in turn on your token cost and token efficiency. You need all the sources. You can't. I don't think ultimately you can cherry pick. You need to use what's available. If tomorrow we run into a gas constraint, we're going to be building solar power data centers.
Yeah, makes sense.
Redundancies.
Yeah, and so we have the energy coming into the data center as a lever. We have the way that we've re-architected the racks as a lever for driving the token, for getting more tokens out of any megawatt that's making its way in. We have some of the innovation around the networking stack, which I'm less versed in. But
I think as you move towards things like optics, and then of course like NVLink to be incredibly fast networking speeds, it's just moving bits across wires faster at that speed becomes incredibly hard, and then taking what is noisy signal off of these wires and finding out what bits they are is a whole digital signal processing that we have some of the brightest minds on to do heroic forward error correction to say, what is that bit as soon as it's coming off? I mean, it's really incredible the detail you can go into on very specific parts of the stack, because then of course cooling, right? Moving towards completely liquid cooled and keeping it at 45 degrees Celsius, which is well over 100 degrees, I think, Fahrenheit. Don't quote me on that.
I'm not going to. Closed loop systems, right? So we're not wasting water, evaporating it into the air, and then having to recover later. I think the other things to look at also that are kind of interesting, but maybe we don't have that much control over. Ultimately, is utilization. Again, if I can keep my factory running, like have it be more productive, then I don't have to pay for the assets that are sitting there while they're not doing anything. They're not just idling. It's not my area of expertise, but financing, right? The CapEx side, if I can find more efficient ways to finance these projects, and if I can deploy them much faster, so that my capital is not tied up for 2 years while I'm building the facility, right? Yeah. That capital is tied up, but it's not producing any output yet, right? So if I can deploy the capital and have it up and running in 6 months to a year, like those are all levers. You guys are totally right. There are things we can do.
All that to bring down the cost of a token. I think that people don't. It's truly hard to wrap your head around the magnitude the level of tokens that we need. And so everything has to be improved. And that's, again, why I think that the cost per token really is the metric that we need to talk about here. Anything else is getting lost in either something that is too far up the abstraction ladder, or you're getting into the weeds of something that isn't actually the meat that drives your P&L.
Totally. And I think just an appreciation for how rapidly the world is changing on all of this, right? All of the use cases are changing. The way that we build the whole stack is changing. It makes sense that we're looking for 5-10% optimizations across the stack. And I think just, an appreciation
Not
for
5-10%, 35x between 35x between different generations. Well, Dr. Prinsloo, thanks so much for coming on and helping us unpack, how power relates to, not only companies' profits, but these new token factories and these intelligence factories that are changing the world around us. And hopefully this is our second of many conversations.
Yeah.
But again, thanks for, it's always fun to speak to an expert on some of these things. Because again, I do think you can go a mile deep on so many different things. This is no longer simple. I think last time you mentioned the e-commerce data centers, where it's a very predictable load. It's racked floor to ceiling with CPUs. We're undergoing, the largest infrastructure investment in history. And so it's going to involve incredible, innovations on the software side, to the chip side, all the way down to the power side.
Yeah, we spoke 4 months ago and so much has changed. Hopefully we get to chat in 4 more months.
I feel like, it's important that we learn from each other. I'm learning every time I speak to you guys. And earlier this year, there was a big utility conference that I've gone to in the past. And for the first time we had serious conversations between utility executives and like data center people. And it was just weird because it was a utility conference, but it was all data, the whole conversation was about data centers. So clearly everyone's learning from each other. The two big industries are coming together because they have to. And it's great to learn. So I appreciate it.
Hell yeah. Well, thank you.
Cheers.